the next theorem, this gives a necessary and sufficient condition for the finite extension to be a simple extension. What is this condition? This condition is given by this Stein's theorem. So this is the naming theorem, okay, and obviously it was given by Stein's. So this is a necessary and sufficient condition. That means if let us first read the statement of the theorem. It says that if E be the finite extension of the field F, so that means you have E as an extension field of F, then the following are equivalent. That means E is equal to F alpha for some alpha belongs to E. So from here you would say that E is a simple extension. And from the second point you say they say there are only a finite number of intermediate fields between F and E. So between F and E, so somewhere here or here or here or here, you would have only the finite number of fields present. So the number of fields which are present between E and F that are finite in number, that could be counted very easily. So this is the necessary and sufficient condition for the extension to be simple extension. That means the given extension is simple if there are only a finite number of intermediate fields between F and E, and on the other hand, if there are finite and intermediate fields between F and E, so the extension is simple. So let us go and look at its proof. Now this is necessary and sufficient condition, and we have to prove the equivalence of these two statements. So that means we will prove that firstly we'll assume A is given to us and we will prove B, and conversely we assume B is given to us and we will prove A. So let us go first by assuming A is given to us. So we will assume that E is equal to F alpha for some alpha belongs to E is given to us, and we will prove that there are a finite number of intermediate fields between F and E. So this is what we will prove. So for that, what we are doing now, because we know E is equal to F of alpha that is given to us, and E is a finite extension. This is already we know. Why E is finite extension? Because this is also given to us, okay. So that means because every finite extension is an algebraic extension, so E is also an algebraic extension, and because it is algebraic extension, by definition all elements of E are algebraic in nature. So in general we will say let this element alpha, which was adjoined to this field F, is also algebraic over F. So if this is algebraic over F, by definition we have some polynomial f of x in f of x such that this serves as the minimal polynomial of alpha. So this is our extension field which is given to be f of alpha, and we have this element alpha belongs to E, and this is algebraic. So by definition we have some polynomial f of x here such that f of alpha is equal to 0. That means alpha is the root of this polynomial. Okay. So now we are to show that there are a finite number of fields in between. So let us first assume that K be the subfield of E which contains F. So it is the intermediate field between E and F. So now we consider some polynomial g of x which is present in Kx, and this polynomial is also minimal polynomial over K of alpha. So that means g of alpha is also equal to 0. This is true because E serves as an extension for this is K also and for this F also. So there is one polynomial g of x here and another polynomial f of x here. So accordingly, because f of x belongs to K of x, so f of alpha is equal to 0. This I told you just now. And because g of x is minimal polynomial over K, so that means, and Px is some other polynomial, so that means this Gx would divide this Px. Here it should not be Px, here it should be f of x. Okay, because f is contained in k, so that means every polynomial which is present here in f of x would also present in k of x. So accordingly, we will say that this g of x would divide f of x. So gx being the minimal polynomial over k, it will divide fx. So now we assume some other extension field k dash, which is the subfield of k and containing f and the coefficients of the polynomial g of x. So k dash is the subfield of k which contains f and the coefficients of polynomial g of x. So that means we are considering some field here k dash in between e and f, which has f and all the coefficients of the polynomial g of x. Then g of x would definitely belong to this k dash x. Why? Because all the coefficients are present in k dash. So we have the structure of fields like this. We have e as here, f here, and we have two intermediate fields here. One is k and another is k dash. We have the polynomial g of x here in k of x and the polynomial f of x here in f of x, and we would say that all the coefficients of this gx and f are present over here, so that means gx is also present in k dash x. So this is what we have said until now. Now because this gx is an irreducible polynomial over k, being the minimal polynomial of alpha, this is also irreducible over k dash because this is the same polynomial. So we would say, because we are given e is equal to f of alpha, this is given to us. So this implies that k alpha is equal to k dash alpha is equal to e. Why? Because f is the subfield of k dash and which is the subfield of k. So ultimately we would say f is contained in k, so from here we could write k of alpha is equal to e, and because f is contained in k dash, from here you could write k dash alpha is equal to e. So all these three, they are equal. Now because this gx is the irreducible or the minimal polynomial in k as well as in k dash, therefore we can calculate the degree of the extension field e over k and e over k dash, and both of these would be equal to the degree of gx because it is the minimal polynomial. So what is the degree? We don't know yet what is the degree, but we surely can say this and this, they would be equal. So if the degrees would be equal, that means the fields would be equal itself. The fields k and the field k dash would be equal to themselves. So next what we are doing, because we have to show that there are a finite number of fields here. There are a finite number of fields here. So we are constructing a set consisting of all the intermediate fields. So we are denoting this by this f, okay, this cursive f, and it contains all the k dash such that what is k dash? It is a subfield of k and contains f dash. So that means it is a family of intermediate fields between e and f. This is one thing. Another thing, we are creating another set, that is S, and the set has all the polynomials g of x from ex such that g of x divides the polynomial f of x which is present in f of x. So that means we would say the set S consists of the set of, it is the set of divisors of f of x in ex. So these are two sets. Now because we having defined them clearly, so now we can define these mapping. The mapping is sigma and it is defined from this fancy f set to the set S by sigma of the field k, which is the intermediate field, that would be equal to g of x, which is the minimal polynomial of alpha over k. So obviously being the minimal polynomial, it would divide fx. So the conditions are fulfilled and the mapping is a well-defined mapping. There is no problem with the mapping. Here k is an element from this set F, and this g of x being the divisor of f of x will belongs to S. Okay, so this is the mapping. So now let's see, this mapping is a 1-1 mapping. How this is a 1-1 mapping? That means for every intermediate field. So this means that 1-1 means for every intermediate field K, we have a divisor Gx in Ex. So this is what we are saying. So here, to show this mapping is 1-1, if this mapping is 1-1, that means this thing is true. Now to show this mapping is 1-1, we will assume that the sigma of k1 is equal to sigma of k2. And what is sigma of k1? This is equal to the minimal polynomial of alpha over f, and sigma of k2 is again equal to g of x. So from here we would say k1 is the smallest subfield of E containing f and the coefficients of this minimal polynomial gx. So that means this thing is also equivalent to k2 because this is equal to g of x. So from here, sigma of k1 equal to sigma of k2 would imply that k1 is equal to k2. Hence the mapping is 1-1 mapping. So this is what we have shown. So now because the mapping is 1-1, so we will make use of this thing and we will say that there exists only a finite number of divisors of fx. Why? Because fx is some polynomial, irreducible polynomial whose factor is alpha. So obviously its degree would be finite. So that means if it is a finite polynomial, so its divisor would also be finite in number. If the divisors are finite in number, so because there is a 1-to-1 relationship between the divisors and the intermediate fields, so we will say that the intermediate fields between f and E, they are also finite in number. So this is one part. For the second part, we have to prove B implies A. So that means now we are assuming that there are, now we are assuming let there are finite number of intermediate fields between E and F, and we have to prove that this E is a simple extension. So for that we again consider two cases. This we had this F, we have this extension field E. Now in the first case this F is finite, and in the second case this F is infinite. So for whenever your F is finite, so in this case 1, we would say, because E is given to be finite extension in the hypothesis of the theorem, so being finite extension, it should be simple. According to the result that we have, E could be written as F into some element alpha, where this element belongs to E. So this is the theorem, and by this theorem this part is clear. Okay, so for the second part, where we have to prove that this E is a finite extension, this E is a simple extension. For that we assume that F is a finite field. So now we will first prove, using this condition that it is an infinite field, we will first prove that for any two elements alpha and beta in E, there would exist some gamma in E such that f of alpha beta would be equal to f of gamma. So we will prove that for two elements this reduces to single element, so that means it would become a simple extension. For simple extension, we will first prove this smaller result, which says that for any two elements alpha beta in E, there would exist an element gamma belongs to E such that f of alpha beta would be equal to f of gamma. Okay, so now for each element A in F, we could construct some gamma A, which would be equal to the linear combination of this alpha and beta. linear combination of alpha and beta, and whenever you change this A, this element would change. Okay. So we have gamma of A defined in this way. So for this gamma A, we would say the fields f of gamma A, where this element gamma A has been adjoined to the field f. For all A, these are the intermediate fields between f and E. How? Because you are now adjoining every element of f. So basically what we are doing, we are saying we have some field here as f. We are taking some element from it, A, B, C, D. There are a lot of elements here present. Okay, so now you adjoin A with it, you will have one field. You adjoin B with it, you will have some another field. You adjoin C with it, you will have some another field. So these all fields would lie in between E and F. So this is the case here. So that is why we would say there would be as many intermediate fields between F and E as there are number of elements A present in F. Here alpha and beta belongs to E, and A is some element of F, and which is also present in E because E is the extension field of F. So now by assumption there are only finite number of intermediate fields. This is known to us. This is the given hypothesis. So this would imply that for two elements A and B which are present in F, because F is infinite, there would be so many elements present here. There would be infinite number of elements here. Okay, such that these two fields would be equal. Why? Because they are finite in number. These fields are finite in nature. If they are finite, so that means f of gamma A is equal to f of gamma B. So taking this thing, we can say that both this, because they are equal, so obviously gamma B belongs to this f gamma B, but because they are equal and alpha A belongs to f of alpha A, because this is equal to f of gamma B, so we will say gamma A and gamma B both belongs to this f of gamma B. So this is from this thing. So that means if they both are present in this field, so their subtraction is also present in the same field. And what was the definition of gamma A? Gamma A was alpha plus A beta, and gamma B was alpha plus B beta. So you could subtract these two, so you would have A minus B into beta. This element is also present in f of gamma B. Now because we have considered this A and B as different elements over here, so their subtraction would not be equal to 0, and we could say that we can then apply this inverse operation, A minus B inverse on this element A minus B into beta. So that means you would have this as beta, E into beta. So this element beta would also be present in this f of gamma beta. And so from here we have beta belonging to f of gamma beta. And what was alpha? Alpha was gamma beta. From here you could write, from this expression you could write alpha, that is equal to gamma beta minus b beta. So now because gamma beta is present in f gamma beta and beta is also present in f gamma beta, so therefore their linear combination is also present in f beta gamma, which is alpha. So alpha is also present in f beta gamma. So using these two relations, you could write both alpha beta are present in f of gamma beta. So that means when these elements alpha and beta, they are adjoined to f, that is also present in f of, because being a field, it is contained in this field f of gamma beta. So this is our equation number 1. And moreover, because gamma was the linear combination of alpha and beta, so this gamma is present in this field of alpha and beta. So that means the field, when you adjoin this gamma beta to it, is contained in f of alpha beta. So this is your equation number 2. So from equation number 1 and from equation number 2, we can have this equality here, and we can say f of gamma beta is equal to f of alpha beta. So this is what we were intended to prove firstly here. that for any two elements alpha and beta here, for any two elements alpha and beta here, there is some another element, for any two elements alpha and beta here in E, there is another element gamma here in E such that f of alpha beta is equal to f of gamma. So this is what we were to prove here. Okay. So next, now we have to prove that the extension field E, that is a finite extension. So for that, E is given to be finite. We have to prove E is simple extension. We are given that this E is finite extension, so that means the degree of E over F is given to be finite. So now if its degree is given to be finite, we can construct a whole lot of extension fields F of U. So there we have F, there we have E, and we have some intermediate fields here present. Okay, so we say the degree of one such intermediate field E over F for all the elements U belonging to E, because there are infinite number of such elements U belonging to F, not E. So you could adjoin this element with F. So you would have F of U1, F of U2, F of U3, and so on. So these would be the intermediate fields. So all these fields would be defined by this set, where this set is the set of positive integers. Why? Because it defines the degrees of the given extension fields, and this is bounded above by this field E over F. So this we have we are defining this thing to be true. So now we assume one simple element U0 belonging to E such that the degree of f of U0 is equal to the maximum of all these degrees. So that means this is the upper bound of this particular set. This is the upper bound of this set. So we have to prove that E is nothing but f of U0. So if possible, suppose this is not true. If this is true, that means we have E to be the simple extension. So we go by the method of contradiction and we assume that E is not equal to f of U0. So that means f of U0 would be a subfield of E, and there exists an element x in this field E minus f of U0, because E is not equal to f of U0. So obviously f of U0 would be a subfield of E. So there would be some element which is present in E but which is not present in f of U. So we assume that a particular element to be x. So by assertion, there would be existing for these two elements x and U0, there would exist some third element t such that f of t is equal to f of x U0. This we have just proved for alpha, beta and gamma. So accordingly, because x and U0 they are present in f of t, and f of u is not present in f of t, because x is not present in f of U0. So from here we could say that what is the degree of this f of t over f? F of t, here we have f of t, here we have f of U0, and here we have f. No, I'm sorry. Yes, by construction this is this thing. So f of t over f, this would be equal to the degree of f of t over f of U0 and f of U0 over f. And this thing, their product would obviously be greater than the one degree of one particular polynomial. So what would be this thing? This degree would be greater than this particular degree. So from here you saw that this degree is greater than this degree, but in here we have supposed that this degree is the maximum degree. Here we have supposed that this is the upper bound for this particular element. This is the maximum degree of this particular set. So here we have this contradiction. So according to this contradiction, we have our assumption that E is equal to f of U0 is not correct. If this is not correct, our assumption that E not equal to f of U0 is incorrect, right? If this is incorrect, so that means E would be equal to this quantity. So E would be the simple extension.